streaming. Okay, so the other day, if you guys have questions about the homework assignment, we can start with that. Otherwise, I would like to kind of continue with what I was about to talk about before the guest speaker came in. Okay. So we'll go back to that website called Digikey, which is a really interesting website. It may not be very interesting to computer science people, but for computer engineering and electrical engineers, this is really kind of like it's like candy store because they sell all kinds of electronics, everything from high output LEDs, like the chips, the driver chips for LEDs, all the way to microcontrollers, to Arduino boards, to that sort of thing. So integrated solutions as well as individual components. Yeah.
Do they sell solar panels by any chance?
Well, if you search, they might. I don't know what. When I check this site, I usually do not look for solar panels. I have not looked for that over here. So we'll give it a try. They probably sell chips or circuit boards for solar panel charging and whatnot. So they have connectors, solar cells, connectors, crimpers, special tools. They even have robotic kits related to solar. So they have 115 solar cells. And one of the best things about this particular website is the search is parameterized. In other words, you can search by watts, power of the solar panel, and they go up to 50 watts. So it's good size, but not like household size. So are you looking for something like that?
My friend's in electrical technology or whatever major.
Okay.
So
electronic technology.
Yes. So he said if I have the parts, I could build like my own little solar panel charging station for you go camping or something.
Oh, okay. Well, I think 50 watts is probably enough for camping purposes. So if you click on a particular criterion, you can say apply filters. You can also apply more than one at the same time, but 50 watt, that's probably only one single item. So 2 can ship immediately, and the price is pretty pricey. Unit price is $500 something. But if you search for something of a lesser wattage, like between 9 and 10 watts, which is okay for charging USB devices, they may be less expensive. So, so right now we have. I cannot see how many items meet this requirement, but there are multiple. But you can.
Top left.
Top left. Okay, two results. But you can also see the pricing. Usually is disclosed here too.
It's $80 for the top one.
Yep, $80 for the 9-watt version, and the $18 version is obsolete, so they do not carry that. If you're looking for robotic stuff and just kind of more consumer type of electronics, there are many other websites too. Okay, I'm trying to think of the website that I order some of my electronic parts, like Bluetooth chipsets. Huh? Smartfun. There you go. Okay. So Smartfun is another website where they carry a lot of Arduino boards. So solar panel, maybe they may have it too. So over here they got the 9-watt solar panel for about the same price, 40 bucks. Oop, no, 90 bucks, 80 to 90 bucks. So I'm not sure whether this is actually the right price, because you might be able to find actual consumer items that is already a finished product for maybe about the same price. I don't know for sure. But on Thursday, we were not looking for solar panels. We were looking for microcontrollers. Okay. And we were looking for, ATtiny to be more specific. Okay, so we are looking for ATtiny products. They're called microcontrollers. they're basically a computer on a chip, which includes the flash ROM for the program and RAM for variables, the stack, and so on. And we were looking at one of their least expensive and also the more limited versions. So we were looking for something that only has 512 bytes of program space, which is about the same as our toy processor. This one, I want to look for only active parts, so there are still 22 parts remaining. So when you look up the prices, okay, this is the column for the prices. If you order 4,500 or more at the same time, they are, each one is 28 cents, 29 cents, let's call it 29 cents, 30 cents. So that, one cup of, Starbucks coffee is like 10 of these things already. Okay, so this is an interesting thing because it means that these chips being so inexpensive, they can go into just about any product. Okay, you can add intelligence or limited intelligence to just about anything. So what we'll do is we'll take a look at the part number here, and this particular chip is really small too. If you look at the physical size, it's really small. If you look at your pinky, okay, the fingernail on your pinky, you can figure, you can probably, if you leave no gap between the chips, you can put 4 of these things on the fingernail on your pinky. They're that small, okay? And this is not even the smallest package that they have, but it is a package that you can still hand solder because it's got leads on the outside and it has a certain thickness to it. They could have made these things a lot smaller, a lot flatter, and a lot smaller. So as a computer engineer or an electrical engineer or a computer science or a developer who's specializing in embedded software, the first thing you need to check out is what we call the data sheet. So the data sheet is here, which is usually a pretty long document. It talks about the instruction set, it talks about the hardware features, it talks about how do you make use of something like this. So this is what they call a low power CMOS. Okay, CMOS is basically the technology of just about everything silicon these days. It's an 8-bit processor. It runs at about 1 MIPS per megahertz. But since it can run all the way up to 12 megahertz, that means it has a throughput of 12 million instructions per second, which to you guys will sound like, what? This is like maybe a few, not even 1% of what my Pentium processor can do. And these are 8-bit instructions. It can only process an 8-bit integer at one time, whereas your Intel processor can deal with 64-bit integers at a time. So what's up with these things? Well, you kind of have to put this into context. Back in the days when the Apple II computers first came out, okay, was that a really long time ago? You can ask your parents. Your parents will tell you, no, it's not that long ago. I was a high schooler at the time, or I was in elementary school or middle school, okay? But it's not really that long ago. Okay, I'm just just for nostalgic reasons, I'm gonna look it up. So we're looking for the Apple II, and the 2 is usually written with the closed square bracket and then the open square bracket for whatever strange reason. Okay. So Apple II series. Okay, that's what it looks like. Good old monochrome monitor. 2 floppy full height. Full width, these are 5¼ inch floppy drives. You need 2 of those because you need to make copies of your games. So you need one to read and the other one to write. Okay, and this is the computer. But what I'm really interested in is the processing power of these things. So we'll look for the processor, which is called the 6502 processor. Okay, so this is the 6502 processor. It runs at 1.23 megahertz with 4 kilobytes of RAM. Okay, you might say, well, okay, so how many MIPS are we talking about? In other words, just knowing how fast the clock is running is not necessarily telling how many instructions it can execute per second. Being an older processor, the 6502 is not pipelined. which means it cannot do multiple things at the same time. So the throughput is actually much lower than the clock speed. You can probably divide the clock speed by at least 3 or 4 in this case to get to the actual MIPS, million instructions per second. So we are talking about a 250,000 instructions per second. And that's it. That's the best this kind of processor can do. So, and it is pretty big too. The processor by itself is a big chip, about yay big, and it emits a lot of heat. And this is back in 1977. To you guys, or to some of you, it is a long, long time ago. But if you think about 77 to 2017, we are talking about how many years in between? 40 years, right? Well, 40 years sounds like a big deal. But if you compare a vehicle from 40 years ago to a vehicle today, I mean, the vehicle today obviously will win hands down in terms of power, torque, handling, and whatnot, but not by this kind of factor. Okay. Now, what is even more significant is the chip that we are talking about here. You can easily put one on a drone. I mean, this weighs next to nothing. Okay, if you need to automate something like rotor control, or stability control, and this processor can actually get it done because it's kind of limited in many ways, it weighs next to nothing. As opposed to an Apple II computer, which is really clunky, heavy, takes a lot of juice to run, and so on. So when we look at this thing, we'll look at some of the specifications here. Operating voltage is from 1.8 to 5.5 volts, so it can go as low as 1.8 volts. At 1.8 volts, it can only run at 4 megahertz, or you get about 4 million instructions per second as the execution throughput. 1.8 volts is not much, okay, because one AA alkaline battery can give you 1.5 volts optimal, and it can run all the way down to about 1.1 before you say, okay, this battery is dead. So you need 2 AA batteries or 2 alkaline batteries to power up this thing. If you're using a lithium-ion battery, which discharges from 3.7 volts down to about 3 volts-ish, you can run at the next tier, which is 8 megahertz. If you have 2 lithium-ion batteries, and then you use a regulator to regulate down to 4.5, about 5 volts optimal, then you can get your 12 MIPS per, 12 million instructions per second, which is really quite respectable if you think about how small the chip is. Okay. Okay. So the next portion is even more interesting. It talks about the power consumption of something like this. So at 1.8 volts, which means it is probably running at about 4 megahertz, it consumes 200 microamps at 1 megahertz. Okay, so what is 200 microamps? How do we look at this number and say, okay, if I give it 2 AA alkaline batteries, how long is that going to run? You do some math, right? Okay, so we'll go ahead and do some math here.
I think they are measuring it in milliamp hours. Milliamp hours? That is what you want.
These are micro, yeah, so milliamp hour is related because you can see the amp, but the hour is the time, right? So you have to do the division. You have to divide the capacity of your battery by the current draw of this thing, and then the time usually will tell you how much how much runtime, how much time you can run this thing at full speed. So I'm looking for my okay, I'm just gonna start it from here. You guys cannot see it yet. I'll bring it up. The reason why I'm bringing this up is, in order to make use of a chip like this, you have to program in assembly. There's no way you can write a C program, let alone a C++ program, to run on something like this. And yet, there are many ways, to make use of these chips. I lost my, Stadler pencil, pencil. I have to kind of go back to my usual, tablet pen here. I probably lost it in the trunk somewhere. Okay, so I'm just going to use this slide here. So we'll do the math. So the math is okay. So the power consumption is 200 microamps. So we write down, I'm writing down here, you cannot see yet. Okay, I'm switching back so you can now see. So we are looking at, this is the actual current draw. And then we want to look at the capacity, the charge capacity of a alkaline battery. So you can look it up. Do you want to look up the AA or the AAA, the AAA batteries? AAA, okay, so we look up AAA. We'll use the usual, cost-effective alkaline batteries. Alkaline battery capacity. Okay. So right here, there's a good summary. Alkaline has about, let's call it 1,000. Would that be fair? It's kind of the average, okay? So we switch back to this slide here. Oops, not that one. This one here. Okay. So we're basically looking at 1,000 milliamp hour divided by 200 microamp. You might go like, oh, so that thing can last for about 5 hours and then we're done. No, because one is milli, one is micro. They're off by 1,000 fold. So we're talking about 5,000 hours. Okay, so it means, if you're not using anything else, you're just running the processor itself. If you just use 2 AAA batteries, okay, which doesn't take up a whole lot of space, it can power up this processor at 1 megahertz for 5,000 hours. So 5,000 hours, is approximately what, 25 days-ish? Let's call it a month. That's not too bad. And this is running at full speed, not full speed, but it's actively doing stuff at 1 megahertz. Okay? But a lot of stuff does not require that, like my Fitbit. Okay? Yeah, go ahead.
Oh, and it says that it also has idle time.
Yep, idle current and also low power consumption. But this is at full speed. This is fully active. It's executing instructions at only 1 megahertz. Okay, when it runs at a higher clock rate, it will consume slightly more power. Okay, but this is still respectable. So we are going to say this is approximately, a month.
It's 200 days.
Is it? Okay.
1,000 hours.
Oh, 5,000 hours divided by 4. Oh, right, okay. My bad. Okay. I thought there were 300 something hours per day. I wish, right? 24 hours per day. Okay, there we go. Okay. So 200 days. That's like more than half a year. And that's on 2 AA, AAA batteries, not even AA. AA is about at least twice as much of juice. Okay, cool. But then you look up we continue to read this, the specification here. It also has idle mode and also power down mode. Now this is where the halt instruction comes in handy. Because when this particular processor executes the halt instruction, it is in idle mode. So when it's in idle mode, it is only consuming 25 microamps, which is 1/8 of the original one. So if you keep it in idle mode for a long time, it can actually extend the battery life significantly. So even if you think about, okay, I'm going to keep it in active mode only maybe 1/8 of the time, 7/8 of the time I'll keep it in idle mode, that will easily extend it to like a year or two on 2 AAA batteries. So if you put something like this on a drone, where most of the power consumption is to turn the rotor, it's insignificant. It doesn't, it doesn't weigh much. It does not consume a lot of energy, and yet it has some processing power. What kind of processing power are we talking about? What do we use these chips for? What do you think?
Could accept remote control.
Okay, it can decode your RC remote control signal and translate that to something that the motor controller can understand. It can control the motor itself. Okay.
LEDs probably.
Also, okay, so idle mode. Okay, let me get back to idle mode. Idle mode means the chip is for the most part powered up, but it's not clocking. So the clocking mechanism has stopped. And that usually is what happens when you put it into a halt mode or when it executes the halt instruction. So when the processor executes the halt instruction, it says, okay, I'm not doing anything. Okay, the ALU is inactive, the registers are inactive. It will keep the content, but it's not actually doing anything. It's not clocking. Power down mode, means it will retain the memory in RAM. It will maintain the registers, but it is not doing anything. So the difference between idle mode and power down mode is when you're in idle mode and you want it to start running again, it doesn't take any time. It just clocks right away. When you're in power down mode, then it will take maybe 5 to 10 milliseconds for the whole thing to start up again, because the clock needs to quote unquote spin up to get to the 1 megahertz range. So so from power down mode, it would take a little bit more time to spin it back up again. From idle mode, it takes no time to continue execution. Yep.
When it runs the halt instruction and it's in an infinite loop, how do you get it out of that?
Aha! That's a very good question. How do you get out of the halt instruction? Interrupts. So the halt instruction, even though it doesn't do a single thing, it is still listening to the interrupt. Now the toy processor at this point does not have external interrupt lines, so there's no way to get it out of the halt instruction. But an MCU like this, it is very heavily dependent on interrupts. So the external hardware interrupt is what is going to get the processor out of the halt mode. And not only that, when the interrupt returns from interrupting the halt instruction, it's going to the next instruction. So not only does it wake up and perform what the ISR or the interrupt service routine is supposed to do, but it will also continue to execute the rest of the program. It will just wake it up and go like, okay, let's move on, until it gets to the halt instruction again.
So it adds to the increments to the program counter?
Yes. So when the interrupt mechanism saves the return address, it's not saving the return address of the halt instruction itself. It is saving the return address, which is the instruction right after the halt instruction. So that's why when the ISR returns, it returns to the instruction next to the halt instruction, which basically resumes execution. So it's really kind of handy. Cool. So you can look up all the pin descriptions. Okay, we'll look up some of the pin descriptions here because we want to understand, okay, it only has, some of these only has 6 pins, right? 6 individual electrical connections. What can you possibly do with 6 electrical connections? 2 of these are dedicated to power and ground. Okay, you cannot avoid that. Okay, that's got to be the case. Port B is a 4-bit bidirectional I/O with internal pull-up resistor, individually selectable, Okay, so what this means, is port B. Okay, these 4 pins can be used for driving outputs, can also be used for sensing input, and without using additional components. So if you have an alarm situation, or if you want to implement an alarm mechanism, this can be connected to a switch, and it will be able to detect whether the switch is open or closed without an external resistor or any additional circuitry. You can also drive the pin. In other words, you can drive the pin to either ground, which is 0 volts, or you can drive it to whatever supply voltage is, which is at least 1.8 volts. So that can in return be used to control a transistor. And then the transistor can switch a much bigger amount of current to turn on LEDs and stuff like that. But if you need to control motors, then you need additional circuitry for controlling motors. So you have 4 individual bits for that purpose, and that's it. Okay, so that's the entire chip. How do you program something like this? Obviously, you cannot hook up a floppy drive to it, like an Apple II computer.
Should we connect it to a pin board or something?
The reset signal is also significant, because you can use it to control the programming of this particular chip. So this thing is in-system programmable. You do not need to remove it from the circuit board, put it into a special contraption to program it. You can program this thing in circuit inside the PCB, but you do need an external header to control the reset pin and also a few of the other pins. The exact mechanism to do it, is described in its own section. The slightly bigger chips, just have two NC or no connecting the pins. So the smaller chips, is using every single pin for various purposes. And most of these pins, have dual purpose. You can see, this pin here, PB0, has many descriptions. And one of these descriptions, TPI data, means this chip can be used to communicate with other chips. So if you have a compass chip, okay, or a accelerometer chip, they talk in either the I2C protocol or they can talk in the SPI protocol. But this chip can talk to other chips using serial protocols, which is really kind of interesting. It has got ADC 0, ADC 1, ADC 2, and ADC 3. Does anyone know what is an ADC? It stands for analog to digital converter. What does that mean? Now, when you look at chips like this with a single pin, most of the time, at least in the good old days, they can only sense, is the pin experiencing a high voltage or low voltage. It will give you a 0 or 1. Okay, so it's not really analog. It is completely binary digital, 1 or 0. Analog digital converter means you can actually tell between 0 and 512. Okay, what is between those two range? What is the number? Okay, so if 0 volt is actually the number 0 and 1.8 is the number 511, any number in between is basically just scaling off of the actual voltage that the pin is experiencing. Which also means the chip can now be used to read thermistors, to read temperature. It can read off humidity sensors. It can read off anything that has a range of voltage, which is kind of cool. Okay, because this is a tiny little chip, and yet it can do all of these things. But since it only has these limited number of pins, each one has it has many things. So you can only choose one for it to do. OC is interesting too. Output compare. That's the name. That's why it's called OC. But it can be used to generate pulse-width modulation waveforms. Now, what is pulse-width modulation? Okay, switching back to here. Okay, so most of the time when we look at the output of something like this, it's either on or off. Okay, and then in software you can turn it back on again. You can turn it back off again. Okay, so duty cycle is basically looking at the amount of time that it is off, or the amount of time that's on. Either way is fine because they're complements of each other, versus the entire period of the two falling edges. So the proportion of time that is on or off, over the entire wave is called the duty cycle. Okay? Why is that important? Why do you think that is important? Yep.
One experience is you can change the duty cycle easier than changing the voltage.
Exactly. Okay, very good. Okay, it is much more difficult to change the output voltage of something because that requires a lot of circuitry, and it is also not power efficient. Okay, I'm not going to get into the physics of why cutting the voltage is not power efficient, but this is much more efficient. You turn something on 100%, or you turn it off 100%, but you control the timing to make it, go like, okay, the average is about a half, or the average is about a quarter, and so on and so forth. Okay, but then you will go like, but then you will see the blinking, right? If you use this mechanism to control an LED, then you will see the blinking. Well, it depends on the period. Okay, if this length of time here is a second, oh yeah, you're gonna see it blink. If it is a quarter of a second, you will see you can still see it blink, but then you go like, okay, but I can't really count the blinking anymore, but I can see it's blinking. If it is 50 times per second, you will still be able to see it blinking if you sweep your eyes. Okay, you will see the dot 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 dot. Okay, but otherwise, if you just stare at it, you won't see it's blinking anymore. If it's at 5 kilohertz, in other words, if it's blinking, but at 5,000 times per second, you cannot perceive it anymore. So this is, so this means, this particular chip can emulate analog output by using pulse width modulation. So you can make something glow. Okay, if you use it to control, let's say one of those portable candle things. They sell these things at Costco and whatnot, right? I mean, you put in like a few batteries. It's completely self-contained, and it will just kind of flicker and glow like a real candle. This chip can do it now because of the output control output, which is emulating pulse width modulation. Yep.
I took a MT class and we were making the motor, servo motor, go faster or slower with the changing of the duty cycle.
Not the stepper motor. A stepper motor is not controlled by duty cycle. It is controlled by the actual stepping. So that's a little bit different. Yeah. Stepper motors are really cool in many ways, but they are also very inefficient.
I was saying servo motors.
Oh, servo motors.
Yeah.
Okay, now servo motors are also different because when you're talking about RC remote control servo motors. Okay, so but it's worth mentioning because we can also look at what this chip can do with those motors. Okay, so when you go to a RC store, how many people are remote control toy addicts? Because people can easily sink like $5,000, $6,000 into remote control toys when they're serious about this. No one here? Okay. Okay, so when you look at an RC servo, okay, this is what an RC servo looks like. They can range in price, from even $10 or less to something that's a lot more expensive. So this is a servo motor. It has got a connector. The connector looks really, really simple because it only got 3 wires: power, ground, and control. So the power and ground is basically just hooking up to a 5-volt source, which can supply a lot of current because it's a motor. Ground, which is just 0 volts. But then the control wire is the one that is doing the controlling. So how do you control a servo motor to go in one direction and how fast, or the opposite direction and how fast? It's all done by pulse width modulation. So the way it's done, okay, I'm just explaining all of these little things here. Okay, so the way it's done is it doesn't look at a duty cycle per se, but it looks at the amount of on time. Okay, in other words, this amount of time is irrelevant. It doesn't care. It is this amount of time that it actually cares. So with a small amount of time, if it is within a certain range, or if it is a particular number, it is considered 0. When the motor does not turn, it is supposed to be just holding at a 0 position. When it is wider, then it goes in one direction. When it's narrower, it goes in the opposite direction. So a servo motor is supposed to be position control, not speed control. So the way the parallax, I guess the bobots, right?
Yeah.
Yeah. So the bobot is basically abusing RC servos so that they try to do speed control by because these servo motors have feedback mechanism. It kind of knows its position. So if you try to make it go, okay, so let's say this is the 0 position, okay, and you send a signal to make it go like this, okay. If you try to apply torque to push it back to the 0 position, it will resist. It will increase the amount of torque going this way because it wants to be in this position. So it has either resistors or an optical encoding mechanism inside the motor itself to know that, oh, I need to be here, but I'm actually here. But someone is resisting me. I'm going to continue to increase the amount of current to push this way until I'm here. So the parallax thing is really abusing this ability. So it's a very weird type of speed control. It doesn't really, it's not linear at all. And it can also vary from motor to motor. But the bottom line is, if you want to do some animated Halloween costume, you can get servo motors, a few chips like what I just kind of talked about, and have at it. I mean, seriously, you can have a Halloween costume next year. Okay, it will take you some time, so start planning now, and you can have your Halloween costume that has fully automated stuff. You can even hook it up to like a motion sensor. So you can have a motion sensor pointing backwards. So if someone is trying to jump you, your Halloween costume will respond. Stick up some spikes or whatever. I would not consider, you know, you might have legal issues if you use a microcontroller like this hooked up to a motion controller and then a AEG, airsoft AEG. AEG stands for automatic electric gun. Okay, do you guys play airsoft at all? No. It can be expensive, yes. So an AEG is basically, they usually look like a replica of some actual weapons used in the military. But the AEG is kind of interesting because they're electric. And anything that's electric can be controlled by a controller like this easily, right? Because it's just a switch or a relay to turn it on and turn it off. So you can easily control, you know, or position an AEG, hook it up to a controller and the motion detector thing. So if someone walks past a certain point, it goes like. I mean, yeah, the possibilities are out there, okay? Because you know we have everything, almost everything is now electric. All right. So getting back to the programming part, okay? So we kind of digressed. Oh, okay, so we can actually buy this for how much? $12 plus tax. That's kind of expensive, a little bit on the expensive side. All right, so getting back to this chip here. The instruction set is something that we also want to kind of examine because you know that's the whole point of this discussion. So we want to go to. The programming part has to do with how do you change the program. So it's a memory programming. This is how you hook up an external programming device, you know, through a 6-pin controller, so that you can change the program on a chip like this without desoldering it, which is really cool. Okay, because if you say, you know, I want to change the way my Halloween costume operates, you don't have to desolder anything. You just reprogram the thing in place, you know, and you're ready to go. Just need a laptop computer with a programming interface, and you can change your costume. We're looking at instructions. That's what we're looking for. So, instruction set right here. Okay. Mnemonics. Okay. Serial load from data space. That's not. This is a whole different instruction set from the one that I'm used to. But when you look at the opcode, do you recognize something that we see, or even the notation? Do you see any notation similarity?
Yes. Would SLD be like LDI or LD? What was that?
SLD is serial load from database using indirect addressing. So that's our LD instruction, or analogous to our LD instruction.
SSTPR.
Sorry? Yeah, that's ST for store, right?
SSTPR, that's kind of funny.
STTPR, store, serial store to pointer register using direct addressing. That is ST. We don't have that instruction. It's STI basically. So it's kind of like a store, but you specify exactly where you want to store using an immediate constant. So we don't have that instruction in ours. Serial in from data space, that one we don't have either. So when you look at this, you know, because of the I/O, your bracket A, the toy processor does not have a total I/O space because we don't have input-output devices hooked up. So we don't have an I/O space. Let's see what else. Okay, serial key. These are. But these are all specific to the programming part of the thing because you know it's not. These are not the actual instructions. These are for programming. I think. So instruction set summary. "16 general purpose registers." Okay, 80 tiny 4. Okay, let me look it up because this is actually what. Does this look slightly familiar to you?
Yeah.
Except for the name, they call it the status register. Except we call it the flags register, right? But it has most of the same flags. It has got the carry flag, the 0 flag. It's got the negative flag, which is our sign flag. Has got the overflow flag, which they call the V, we call it O. Okay, it doesn't have the L flag, which they call the S flag. Look at the S flag here. N, which is the sign flag. Exclusive OR with the V, which is the overflow flag. That's the L flag. In other words, they changed the names a little bit, but they got the same flags that we do. They have a half carry flag, which is kind of weird. Typically, people don't do 4-bit calculations anymore, but it's only good for 4-bit calculations. Transfer bit using these specific instructions. And there's a global interrupt, enable, and disable. In other words, if you have a section of code where you say, I cannot handle interrupts between this chunk of code, between here and here, then you disable interrupt before you get into that section, and then re-enable interrupt after you exit that section. It is actually kind of important because this is how you can guarantee certain operations to be atomic. It's only important when you're dealing with interrupts. If you don't have interrupts, obviously you don't need to disable interrupts. So it's got registers, constants, which is our I, okay? And when you look at the actual instruction set, okay, so it's got, okay, these are the actual instructions. It has add with carry, we don't have that, but it does have add, just regular add also. So when you look at the regular add instruction, and you look at the operation, the notation is slightly different because I use the C notation, whereas this one just uses a left arrow instead of an equal symbol, okay? But it's kind of the same thing. You add up 2 registers, and the sum is stored into one of the registers, the destination register, and even the order is the same, okay? You can see the destination register is the one, the first one, or the one to the left, which is the same as our instruction set.
Program counter.
And then program counter increments, exactly. So it also has, as you can probably imagine, it has conditional branches too. So let's go check out the conditional branches. Okay, they call these branch if blah blah blah. Okay, but this is basically the JCI instruction that we have. Okay, they call it slightly differently. They say branch if carry set. So when you look at the code or how it describes it, this one is a little bit different because it adds an offset to the program counter. It's not just, okay, take that byte and that becomes the destination address, but it takes an offset. But that also gives it a certain limitation, doesn't it? Because now a conditional branch can only branch to a location. The new location has to be either 64 instructions before or up to 63 instructions ahead. It is no longer absolute. You cannot just say, I need to go to that instruction over there, which is a long way off. Can't do that. But it's a limitation, because the trade-off is what's worth it. Okay. The ADR architecture is interesting in many ways because it's a completely new architecture by the time when it was invented, which was the 1990s, okay? Early 1990s. But when they redesigned the instruction set, they did not go to the extremes. In other words, they did not just copy all the existing processor architecture at the time, which were mostly CISP architectures. But they did not go to the opposite extreme of complete RISC just because of philosophical reasons. They did a kind of a balance between the two. And the balance, interestingly, is based on C compilers. So they chose the instruction set, they push and pull, they optimize the instruction set, so that the compiler can generate code that is optimal for execution. So that is kind of interesting. You know, it will be interesting for those of you who are going into computer engineering, because that's basically what you do, is you have to make trade-offs. Okay, should we implement this instruction or should we implement that instruction? What is the trade-off? Okay, is it significantly going to help the efficiency of program execution? Is it going to help the compiler compile your code? That's the trade-off. And you know, AVR did a pretty good job with that type of trade-off. All right. So it has got the branch if equal. That's our JZI instruction. So when you look up the description here, it says if the Z flag is a 1, then PC is PC plus K plus 1. Otherwise, PC is just PC plus 1, which is just the next instruction. Okay. All right. Interestingly, this processor does have the call instruction. So the call instruction, if you look at what the call instruction is doing, it can only call, it can't call within the entire memory space, 64 kilobytes. The program counter is getting the K, which is a constant, which is our immediate, and it also performs stack operations. When you look at the stack operations, what does that remind you of? Whatever the stack pointer points to gets PC plus 2, which is the instruction after the call instruction, because the call instruction takes up two words, and then the stack pointer is decremented by 2, because that location is now used to store that the PC plus 2. This particular stack pointer is not the same as our stack pointer in that it does not point to the last thing that we point to. It points to the next available location to store something. So it's off by a little bit. Is that okay? So if they have a call instruction, which other instruction do you think you can expect?
Return.
Return, exactly. So we'll look up the return instruction. Yep, it's got LDI. It's got LD or LDD, which is load indirect. So it has got our processor is a lot simpler than this one.
No recall.
Hmm?
No return. There's a recall before it.
So the return instruction, is just incrementing the stack pointer, but the PC or the program counter it will read directly from the stack, whatever the stack pointer points to the program counter, and then it will increment the stack pointer, which is also what we do with our processor. Is that okay so far with this stuff? Okay. But prior to today's lecture, you probably have not even heard of the AT-Tiny family of processors. It's not mainstream, okay? But just because it's not mainstream does not mean it is not useful when you are considering your career choices. Because it is inexpensive, 28 cents each, okay? The small size, the power consumption is really, really low, and the versatility of this thing, it can go into many, many applications. So when you think about it that way, there are more possibilities with this kind of controller chips than there are possibilities with phones, with mobile apps. You would think like, wow, there are tons of things we can do with a mobile device, but there are more things we can do with these things because they can go into something that does not even resemble a computing device. What do I mean by something that does not resemble a computing device? I mean, who would be your employer if you say, I'm the top-notch microcontroller expert? I can make designs that are cost-effective. If a 50 cents part is all it needs, I can make that 50 cents part work for whatever application that you need it to work with. Okay, so if you're an expert like that, you're more likely going to be a consultant rather than being hired by a company. But who will be your clients? Come on, you guys can imagine stuff, right? Come on.
Intel? Intel?
No, Intel doesn't care. Intel makes the chips. Intel will contact you and say, okay, use our chips. I'll give you a discount. Or I'll give you a kickback. So it's not Intel. Who do you think can utilize something like this and say, you know what, our current product line is really kind of dumb. I want to make it intelligent. I want to make it digital. I want to make it Bluetooth connected, la 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 la. And they have no in-store, they have no in-company ability. Go ahead.
Kids' toys.
Kids' toys, okay, that's one. Furbies, right? You can resurrect Furbies.
Small companies.
Small companies, well, not necessarily small companies. What about Mac tools? Go ahead.
You can like automate everyday stuff like lawnmowers maybe? Lawnmowers?
Lawnmowers. Now lawnmowers is a little more specialized because it's more has more integration with GPS, and many other things. But yes, that will require more than just these processors, because these processors are way too simple. It cannot handle like you cannot. They don't have file systems. You cannot say, okay, here's a file of the geometry of this particular lawn. I mean, you cannot remember that. So for a lawnmower, if you want to automate and make a robotic lawnmower, I would imagine you can use some of these chips as satellite processors to specifically control, let's say, the rotor for the main cutter and a few other things. But you will need something that has the processing power of a Raspberry Pi in order to do the main control function, because a Raspberry Pi runs Linux. You have a full file system. You have a TCP/IP stack. You can hook up to Wi-Fi network, and so on and so forth. So with a lawnmower, you need something a little bit bigger as the main controller. But even the Raspberry Pi is how much these days? $30. $30, and it packs a lot of processing power. Okay, a lot more than this. Okay, what else? Come on, you guys can. You're at Home Depot. Okay, you're going through all the aisles like I enjoy doing, window shopping, right? And you look at all the things and go like, does this thing have a processor inside? Does this thing have a processor inside? Does this thing have a processor inside? What do you think has a processor inside?
Sprinkler systems.
Sprinkler systems, okay? The timer of sprinklers definitely have processors. And many sprinkler controllers can now hook up to moisture sensors. So on the day when it's raining or it's just moist or it's cold and the soil is still moist or damp, you can it will turn itself off. Today I don't need to sprinkle. Okay, cool. What else?
Like lighting.
Lighting control. Okay, a lot of lighting controls are way beyond what these chips can do now, because a lot of lighting control are they're hooked up to a network with a controller that is managing everything. They use ZigBee as a communication protocol, not Wi-Fi or not Bluetooth, but they use ZigBee as a control mechanism. ZigBee, I think, okay, I'm not sure whether it's spelled this way, but it is. Okay, so ZigBee is interesting. If you have not heard of this term, you might want to look it up if you're interested in automation and stuff like that. ZigBee is a low power, long range type of communication protocol. The main difference between ZigBee and Wi-Fi is it is also decentralized. Okay, the range of ZigBee depends on the closest ZigBee module, not the router. Well, what that means is, between any two ZigBee devices, there's a certain distance limitation. But there's no such limitation of how far is one ZigBee device from the central hub. So that means in order to extend the range of your ZigBee control network, you just have to look at the last ZigBee from where you want to install the next ZigBee. If it is within a certain distance, you're good. Okay, and power consumption is also very low with ZigBee, so that makes it very suitable for like home alarm systems, home monitoring systems, and stuff like that. Inexpensive as well. This company, Digikey International, they actually bought the company that I worked for before I started teaching here. The company that I worked for is called Z-World, Z as in zebra. Z-World, it was a company in Davis, and they got bought by Digi shortly after I resigned from that company. And the chipset is pretty inexpensive. Okay. I kind of lost my train of thought. I got a train wreck in my head now.
You're thinking about with processors are in.
Yeah, in Home
Right, Home Depot, that's right. Okay. Thank you. You guys are my auxiliary stack. You can backtrack a few times and go like, yeah, you were here. That call started from here. Cool. Okay, what else? You go to the power tool section. Okay, what do you see?
Drills.
Power drills, right? That run on lithium-ion batteries. Okay, and you look up a DeWalt device. Okay, and what do you see? What is the okay? So you look at the DeWalt battery-operated drills. Okay, and they have a range of products, everything from under $100 for something, all the way to like $300. What is the difference between the quote-unquote construction or contractor grade versus the homeowner grade?
Contractor one's probably smarter and more efficient.
More efficient, very good, because you don't want a contractor to have to keep recharging the batteries, and lose time. But what makes a power drill motor more efficient?
Like variable motor speed depending on how much torque is being applied.
Okay, that's one. Yep. But there's a little bit more. It has to do with the nature of the motor itself. What type of motors are we talking about? What are the alternatives? If I want to be cheap, okay, and just go for, okay, this is the homeowner edition, I just want to use the least expensive motor possible, they are called just regular DC motors, okay? You might have, encountered those things in your physics class, right? They talk about DC motors. And DC motors are very simple. They use a physical commutator to switch the current around, okay? So it has a few problems because, one, it has a brush, right? It has a brush so that you can conduct current into the coil, which is the moving part. But the brush is always getting rubbed against, with the commutator. So over time, the brush is going to get worn down, and a lot of electric drills, can replace the brush, okay, or the commutator contact, because it's made out of graphite, which is really smooth. It's self-lubricating, but it's also inexpensive to replace. But it's also inefficient. Okay, DC motors like that are very inefficient. So how can you make it more efficient? Did I say brushed with DC motors? So if one type of motor is brushed, what do you think the other types are? Brushless. Okay, all right. So brushless motors are more efficient because they do not have a commutator. The electromagnet is on the outside. The rotor has permanent magnets, so they reverse the whole thing. Is that okay? Just kind of in your mind, you can kind of think of. Now, all of this stuff, we are not in physics class, obviously. Okay, so you have a coil. Okay, wrong tool. So you basically have a coil that is, not moving, another coil that is not moving, and then the rotor itself, the part that actually rotates, is a magnet. Okay, it has several magnets, but for the purpose of this discussion, we'll just say two. And okay, I was wrong about this whole picture. Okay, erase. There are 3 electromagnets. So 1, 2, and 3. Okay. So with this particular design, the magnet itself is the one that is rotating, okay? And it's brushless because there's no electrical contact that has to go across something that moves. So because of the lack of a contact, it is more efficient because you don't have the resistance of the brush, generating the heat, and it's also the longevity of something like this is insane, okay? Because there's nothing to maintain other than the bearing, okay? But bearing is a done science, okay? People know how to do bearings. But how does it relate to this class? It's like, okay, you look at a motor like that, and you look at this class, which we are learning assembly language programming. What is the connection? Where's the connection?
Different electromagnets have to be on and off to make it spin.
Yep. And if you turn one fully on, then it will go in steps, right? It's not smooth anymore. So how do you make it rotate smoothly when you are just barely touching the trigger to rotate very slowly? Instead of having the trigger going, you doing steps like that.
Slight power.
You need post-width modulation. So the ratio of your duty cycle between these magnets is what can change the position of the magnet very, very fine. Okay, it all depends on what kind of duty cycle control you have. If you have 512 levels of duty cycle control, you can make it go almost imperceivably smooth. If you only have like 4 levels of control, 100%, 75%, 50%, 25%, and none, but that would make it 5 levels, then it's going to go, you can kind of tell it's stepping, but not as bad as just fully on and off. That is microcontroller control. Okay, the expensive drills from Home Depot is actually a computer. Okay, how many people have seen those Mac tool trucks? You guys are all mostly computer science people, so you don't really care about those things, right? If you're in the automotive technology department, they go like, oh yeah, candy store, right? Mac trucks, the Mac tool trucks,
There's a Snap-on.
and also Snap-on, those things, get into a auto repair shop, and all the technicians will be flocking over and booing and howling, and going, oh, look at that. Okay, so we're talking about torque ranges. Do you guys know what is a torque range? Some of you do, some of you are like, no. Okay, when you tighten the screw, okay, there is such a thing called over tightening. Which means you can strip the threads, okay? You can destroy the screw itself. I've done it several times myself. Cheap Chinese screws, with really soft metal. I turn a few times and go like, where's the screw? The screw head is on my screwdriver. The rest of the screw is in the hole. They're like, how do I get it up now? Okay, so you need to kind of control or know how much torque you're applying when you're screwing something like that. Or even more importantly, when you change your tires, when you put your wheels back onto your vehicle, you need to torque it. Because too much torque, the lug nuts is gonna strip, okay? It's gonna bind, and then next time you will have to destroy it. Too little, you might be driving on the highway and then find out that you're only driving on 3 wheels. That actually happened to one of my relatives. He lived, the car was fine, but it was very scary. Just imagine that, you're driving and then you're trying to slow down and then you see one of your tires rolling forward ahead of you. You're like, that's not a good feel. Okay, so you need to know how much torque you're applying to the torque range. What does that have anything to do with processors or what we're talking about today?
Processor will be controlling the torque.
Well, it cannot be controlling because because the mechanic has to be the one applying the torque. But the computer can do one thing. Yep.
It can sense the pressure.
It can sense the torque. Yep. And then what?
And then transmit the signal to unlock the wheel.
Well, you cannot quite do that, but you can do one thing that is really, really helpful. You can use an audible tone, okay, to let the mechanic know you're getting close to the set torque, you're at the set torque, you're over the torque. So the mechanic can now listen to the torque range and not have to watch it, and know, okay, this is enough torque. Okay, good, move on to the next one. And because it's electronic, yeah, go ahead.
Sorry, I think that they use something similar that unlocks they have teeth that roll, that spin, and then when it gets over the teeth stop.
There's a mechanical solution to that problem too. But when you're loosening a lug, you might want to measure that too. You want to measure like how much torque do I need to remove something, because sometimes the specification is not published. So you want to record, okay, when you disassemble something, you want to record how much torque you need to disassemble it, so when you reassemble, you can use about the same amount of torque. So that's when the electronic device can be handy, because with mechanics, that's one thing, where their hands are always greasy, right? You put on gloves, but it's always greasy. So you don't want to touch the, you don't want the control device to be on the torque wrench itself. Then what do? Your torque wrench, is basically, it looks like a regular torque wrench, but you need it to be programmable. You need to say, okay, set maximum limit to 200 inch-pounds or whatever, okay? How do you do it? Make it Bluetooth. Now it hooks up to your phone. And once it hooks up to your phone, you can talk to your phone, right? Set torque wrench, limit to 200 foot-pound. Confirmed. Okay, now use it. Yep, go ahead.
Could you put like indicator lights that show the load on the?
You can put in indicator lights too. Yep, indicator lights would be helpful, but then you have to, but then the torque wrench will have a window of some kind to let the LED out, to let the light out. So yeah, I suppose you can do it that way.
Like as it's getting tighter and tighter, it turns more like green to yellow to red.
Yep. Yep. And just to let you know that that we are not insane. I'm not insane and just talking about this. Snap-on digital torque wrench. There we go. This is a Craftsman, but for homeowners and whatnot, you can look at the price and it's a lot less than the Snap-on. Yep, so there you go. It's got a digital display, got a few buttons. Okay, where's my infomercial? There we go. So you can definitely tell from the commercial, this is intended for homeowners. But I will bet you it's not Bluetooth connected yet. So you still need to me this is not a very good design because it's not very durable. You want the torque wrench itself to be completely sealed and use wireless recharging and stuff like that, and then you want the display or the interaction device to be like a cell phone that is somewhere else, because these tools get abused left and right. It's not a very good idea to put an LCD display on it. So any questions about this? No questions? But think of all the possibilities. I mean, we are just looking at a few of these possibilities. And that's why, assembly language programming, used to be thought to be a dead field because we got compilers, okay? We got all of these, really powerful processors. Why do we need to program in assembly language? Okay, there's no particular reason. But when you think about applications like this, or the DeWalt, tool, I mean, you can say that, okay, I can do the same thing with a Raspberry Pi, okay, to control the brushless, DC motor. But that's expensive. Okay, you put in a, even if you just count cost of a Raspberry Pi, you're talking about $8 at least. Okay, so you put an $8 thing into a power drill, okay, which sells for about $300. But of the $300, I would say maybe $100, maybe $80 is the actual cost. So adding $8 to an $80 device in terms of cost is quite a bit. But if you say, but I can make this work with only $3 worth of electronic parts, that's a big deal. So that's why these really kind of low power devices, microcontrollers, still has its place, even though we have Raspberry Pis, we have other types of devices. And then the other thing that I also want to show is, in addition to the AT Tiny, it has got a bigger brother called the AT Mega. So the AT Mega line of controllers can be quite powerful. They can run all the way up to 20 megahertz, but when you look at how much RAM it can contain, EEPROM, so RAM size can go all the way to 8 kilobytes, which to you is not a whole lot, right? my gaming PC has got 32 gigs of RAM. What is 8 kilobytes to 32 gigs, right? But it's enough to have a stack. It's enough to have a real-time kernel. It's enough to implement multi-threading. So these things can actually do quite a bit of complex operations at least for the price that they're they're at. So when you apply the filter, we look at these guys. They're not too bad. About $8.
Is that per thing though?
Hmm?
Is that per chip on the sheet?
It is per chip, and minimum quantity is 1,000. But these can perform significantly more stuff than the chips that we just looked at. So when you look at the pin out of these things, okay, so we'll pick up one of these things, 128.1. I used to use one of these particular chips for a consulting job, and you look at the summary. It has got a lot more capabilities. So it's, when you let me zoom in so you can see a little bit better. Peripheral features. So these things are built into it that you can perform. It has got, I'm just going to point out here, 6/12 depending on which version, because it's got the 128 and also the 256 version. But you can have up to 12 pulse-width modulation channels. You only need 3 channels to control one DC brushless motor. So with 12 channels, you can control up to 4 DC brushless motors to perform basically continuous smooth rotation at very, very low speed. Does anyone want to do an all-wheel drive, rover as a robot? One chip can do all the motion control. On top of that, it can also perform other things. Because with the pulse-width modulation being implemented in silicon, it does not need software. So your software is now free up to do whatever you want to do, what you want it to do. You can use a serial channel to hook this up to a GPS on one side. You can use, then you can actually know the location of the robot. One of these chips is enough to implement a fully autonomous lawnmower. Is it kind of expensive at $8? Well, sort of, but your lawnmower is going to sell for what? At least a few $100. And it's field upgradable too. It's time to download the new firmware for your lawnmower. Any questions? No questions? Okay, now since we all have these smart watches, I just want to kind of go back to the power consumption part. Okay. How much time do you think your Fitbit or your smartwatch is active in terms of proportion of time?
10%. 10%.
I do not know for sure. Okay, but 10% sounds about right. Okay, because I can charge my Fitbit once, and it can run for about 5 days before the next recharge, and it doesn't have a big battery either. So what that means is it's actually going into low power mode most of the time. And it only wakes up and samples stuff, once in a while. But that's because, how fast can I walk? How fast can I do a motion thing so that it matters to this thing? In other words, how many times do you think it has to sample in order to capture my movement? 100 times per second is way too much. Okay, I cannot possibly move that fast. So maybe 20 times per second. So 20 times per second to you is really fast, because how do you count 1 to 20 in a second? You cannot. Okay? But to a computer, it means there are 50 milliseconds between the events. 50 milliseconds is a long time. Okay? Even at 1 megahertz, what is 50 milliseconds? How many clock cycles are we talking about? Let's do some math here. Okay, so we are talking about 50 milliseconds, right? And we are talking about 1 megahertz. Oops, keep switching the tool. I have to go get my other pencil back. Okay, we are talking about 1 megahertz. Okay, so the question is, how many clock cycles are in 50 milliseconds? You just do the multiplication. So it's 1 million times 50 milli, which is 0.050. So that's 20th, right? So we are talking about, if it's 20th of this, it is 500,000 or 50,000. No, that sounds about right. Okay. This shift to 0 by 1, it's over here, and then times 5. I think that is correct. Does anyone want to check my?
Yeah, it's 50.
Is it 50,000?
50,000.
Yeah. So we're talking about 50,000 clock cycles, and if it is 1 clock per instruction, we are talking about 50,000 instructions. Between samples, it can basically execute 50,000 instructions, but it doesn't need to. Okay, there's nothing to do between sampling. So now it can turn itself off. Every 50 milliseconds, it will wake up, sample the sensors. In this case, it's really just the motion sensor. Okay, it doesn't have any other sensors. Keep a log. Okay, store it somewhere. Go back to sleep. So now your duty cycle is really low, and that's why they can extend the battery life. So all of these things are very interesting because it opens up possibilities that I guess traditional developers or programmers do not even consider. So if you're interested in this kind of thing, we are running out of time today. Computer engineering or electrical engineering is what you might want to get into instead of computer science. Computer science, has a lot of interesting stuff too, like AI, big data, all of those things are interesting, and they're, also, that's the future, of computer science. But if you're interested in low-level stuff, like this stuff that we are just talking about, computer engineering or electrical engineering is what we are talking about. And that has a lot of application in robotics, in the Internet of Things, and in automation of just about everything that we can think of. So, is it exposing you guys to more possibilities? May not be something. It may not be your cup of tea. Okay, I used to do this stuff for a living for 8 years, and I really liked it. And at the same time, I was in a graduate school at UC Davis, and my dissertation is an AI topic. So on one end, I'm doing AI kind of stuff, high-level logic, and then on the other side, I'm doing this stuff, like actually working with chips. So it was really nice. I liked it. All right. So I'm going to transition to the lab, and if you guys want to do your homework, I'll be over at the lab to kind of help you guys. The homework is due in a little bit less than 2 weeks now because we got 2 days rolling already. But if you have questions and want to get started, I'll be over at the lab. Yep.
What days are finals?
Good question. Okay, let me see if I can look it up. It should be in the syllabus, if I remember to put it there. Modules. Nope, okay. And there's some course information, probably the last part of it. Oh, right there. So it's on the Tuesday from 8 to 10 a.m.
Then are we learning any new topics between now and then?
Nope, we'll just be focusing on the homework assignment. Basically, that's how I want to help you guys study, is to go through the pins, the chips, the multiplexers, and explain how it works. And then next Tuesday we'll have the practice final, so that I can give you guys an idea of questions that I have asked actually in the past for the final exam. So hopefully that will help as well. All right, so I'm gonna shut down here.
Do you mind putting the previous finals on sheet?
Sure. I think it might have one or two already, but
Yeah.
yeah.
Well, if it is,
Okay.
so at least over this weekend.
Okay. If I have not, just send me an email to remind me.
But now that I think about it, I'm pretty sure.
Okay.
Bitcoins when it started out, they were about, what's it called?
They're supposed to.
Less than $1. Like half or computer saw everything.
I feel like it might help time, but I need to double check my
Also, too, I was gonna ask.
Yep.
So for like computer engineering
Uh-huh.
and electrical engineering, it's mostly based off of this stuff.